All right. So having seen the Frobenius series and knowing how it works in practice, we are now ready to tackle a very interesting and very important differential equation. And this is another named differential equation. This is called the Bessel's equation. So Bessel's equation, just like the Legendre equation, finds a lot of application in engineering problems, particularly problems with cylindrical symmetry. You can also see it, for example, if any of you take an advanced course on quantum mechanics, you would actually see it popping up when you do a scattering problem in quantum mechanics. So suppose if we shoot an electron towards some negatively charged sphere, the electron is going to get deflected. And as the electron moves very far away from the deflecting center, its wave function is going to follow the Bessel functions. So we'll see what the Bessel functions are as we go along. Okay. So for now, we will try and tackle the Bessel's equation and use the Frobenius method to try and solve it. So as we talked about in the last lecture, Bessel's equation is given by y double prime plus 1 over x y prime plus x squared minus mu squared over x squared times y equals 0. Okay. Of course, I can rearrange this by multiplying through by x squared, which is this form. The standard form is usually good to check if something does indeed obey the requirements for a Frobenius series. But as a practical aspect, it's easier to multiply through by x squared. Write this equation as this. Now, in this case, nu is some parameter. I'm not going to restrict nu to integers, at least not straight away. We will talk about nu being integers as we move along, and we will also talk about nu being non-integers. But for now, just treat nu as some kind of a parameter. Okay, so nu is some parameter. We'll specialize to particular values of nu later. Okay, so now this equation follows the requirements for a Frobenius series. So I am okay in looking for a solution of this form. Am x to the m plus r, where I remind you m is an integer, but r may or may not be an integer. So we'll have to figure out r, and to figure out r, we'll have to first write down the in-Bessel equation. So let's move on to trying to figure out what the in-Bessel equation of the Bessel equations is. So again, y prime is given by am m plus r x to the m plus r minus 1, the usual way. And the second derivative is m plus r minus 1. And this brings down 2 powers of x. Okay. To substitute everything back in the original equation. So let's call this equation 1. So you see that x squared times y double prime is going to be such that the x squared kills this factor of x to the minus 2 here. So you're going to get only x to the m plus r. Similarly, x times y prime, the x in front of the y prime is going to kill this minus 1. So you're again going to get x to the m plus r. So both these terms are going to have the same kind of form. So I can write them together. Am, the first term is m plus r minus 1. And the second term, of course, is plus m plus r. The whole thing multiplies x to the m plus r. That is the y double prime term and the y prime term. And now for the third term again has 2 pieces. The first piece is x squared times y. The second piece is nu squared times y. So the x squared times y piece has the form am x to the m plus r plus 2. Okay, because y is x to the m plus r. So I'm multiplying this by an x squared piece. The minus nu squared piece again has the same structure as the first term. Am x to the n plus r. And this whole thing has to be equal to 0. Okay. So now I can combine these two guys and write it in a slightly more compact form. So first recognize that this bracket that I have here is basically, if I take m plus r out common, I get m plus r times m plus r minus 1 plus 1, which is basically m plus r the whole square, right? So I can combine the first term and the third term, and that will give me basically m plus r squared from the first term and a minus nu squared from the last term. So let me do that. So I'll take this off, and I will write this as m equals 0 to infinity am m plus r squared minus nu squared, the m plus r. And the second term is x to the m plus r plus 2. And the sum of these two series has to be equal to 0 to satisfy the Bessel's function, the Bessel's equation. Okay. So now let's go ahead and equate a few coefficients to 0 to see if we can find something nice in the pattern that emerges. So first of all, what is the lowest power of x here? Well, the first series starts with m equal to 0. So the lowest power of x there is obviously x to the r. The second series also starts at m equals 0, which means the lowest power of x here in this series is x to the r plus 2. Okay, so the indecisional equation obviously comes from the first series and not the second one. So let's equate the coefficient of x to the r to 0. So simply put m equal to 0 in the first term, and you would get r squared minus nu squared times a0 equal to 0. Okay, and since a0 is not equal to 0, this gives you an indecisional equation, which is r squared minus nu squared equal to 0, which tells you that there is two values of r that you can look at, plus nu and minus nu. So having looked at the indecisional equation and figured out the possible values of r, we will now move on to looking at the second power also. Now notice that all I have at this point is r that is plus nu and r that is minus nu. Okay, so I do not yet know what class of solutions I should look at, because the difference between r1 and r2 may or may not be an integer depending on what values of nu I choose. So for now, I'm keeping nu arbitrary. Okay. So let's go ahead and look at the coefficient of x to the r plus 1. Again, the x to the r plus 1 can only come from the first series because the lowest power of x in the second series is x to the r plus 2. So which means the first series gives me, for m equals 1, I get a1 times r plus 1 square minus nu square, and this has to be equal to 0. Okay. All right. So again, what is the coefficient of x to the r plus 2? Well, x to the r plus 2 can have two contributions coming from the first series or the second series. In the first series, to get x to the r plus 2, I will need m equals to 2. And in the second series, to get x to the r plus 2, I will need m equal to 0. So which means the coefficient of x to the r plus 2 has two contributions. The first is an a2 times r plus 2 square minus nu square from the first series, and plus a0 from the second series, and this has to be equal to 0. And you can go on in this fashion. Okay. All right. But it is more profitable to write down a recursion relation and figure out the coefficients if possible, if there is a neat pattern that is emerging, and that's what we're going to try and do now. But now we need to choose the value of r before proceeding. So there is two values of r here. So for now, we will look at the first root of the indecisional equation and consider r equals nu. Okay, so this is the root of the indecisional equation that we are going to be concentrating on for now. Okay, all right. So if I put r equal to nu, what happens? Well, look at the coefficient of x to the r plus 1. If I look at the coefficient of x to the r plus 1, I get A1 times r plus 1 square minus nu square equals 0. Okay, what is this? If I put r equals nu, this is basically A1 nu plus 1 square minus nu square equal to 0, which tells me A1 times the nu square cancels here, and I get 2 nu plus 1 equal to 0. The only way this can be 0 is A1 equal to 0 or nu equals minus half. But I have already told you that I want to keep nu completely arbitrary for now, right? So we're not going to specialize to any particular value of nu. Nu could be anything that you give me. So since I don't want to impose any restrictions on nu in general, the only way this can be 0 is if A1 equal to 0. So let's keep this in mind and then move on to the recursion relation. So we want to now look at the recursion relation. So far, we have understood that solving the Bessel equation gives us two roots, plus minus nu. And for the root r equals plus nu, we found that, of course, a0 is not equal to 0 in both the cases. But in the case r equals nu, we have just found out that the first odd coefficient a1 has to be equal to 0. Okay, all right. So having said this, let's now go back to this equation. Let me rewrite this equation. So sum over m equals 0 to infinity am times m plus r square minus nu square x to the m plus r plus am x to the m plus r plus 2 equals 0. Okay. And since we are going to look at r equals nu, let's specialize this to r equals nu m plus nu square minus nu square x to the m plus nu am x to the m plus nu plus 2 equals 0. Okay. All right. So before proceeding, a recursion relation should tell you a condition between two different coefficients, right? So the first thing to do is to massage this equation such that I get two different coefficients. And I can do that by looking at the second series. The second series, remember that since m starts at 0, this series is basically a0 x to the nu plus 2 plus a1 x to the nu plus 3 plus blah, 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 right? Now, in this series, I can write m goes to m minus 2. Why would I want to do that? Well, if m goes to m minus 2, the coefficient of x in this series is basically m plus nu, which is the same as what I have over there. So if I do a change m to m minus 2, what I have here is, I'll stick with green because this is so m to m minus 2. So this is a m minus 2 x to the m plus nu. Okay. Now I should be careful in evaluating the sum. I cannot write m equal to 0 to infinity in the sum with impunity, because this series has to match the series that I have written above, right? So all I'm doing is just a change in the way I label the index. So which means, to be consistent with the series above, this has to go from 2 to infinity. Okay, so I have to keep this in mind. So if I put m equals 2, the lowest power, 2 minus 2 is 0. So this is a0 x to the nu plus 2. And if I put m equals 3, the next term is obviously a1 x to the nu plus 3, and so on and so forth. So this series is formally the same as this series, except that I should remember that this series doesn't contribute to the lowest two powers, right? It doesn't contribute. For example, in the first series, I have x to the m and x to the m plus 1. X to the nu and x to the nu plus 1, but in the second series, I actually start at x to the nu plus 2. So you should keep in mind that the second series doesn't have the first two terms that the first series has. Okay. So with this caveat, let me write this equation down in a form that helps us to understand the recursion relation easily. So so m plus nu squared minus m squared, this term is basically m squared plus 2 nu x to the m plus nu plus am minus 2 x to the m plus nu equals 0. Okay. So I can club everything now and write this as m plus 2 nu, that is the first term, plus am minus 2. The whole thing multiplied by x to the m plus nu has to be equal to 0, which now gives me a recursion relation between the coefficients. So this gives me that am is minus 1 divided by n times m plus 2 nu am minus 2. Okay. So here's where the fun starts. Now put m equal to 3 in this equation. Now if I put m equals to 2, obviously, I will get a2 in terms of a0, right? That is perfectly valid. So put m equals 2, I will get the left-hand side a2 equals minus 1 divided by 2 times 2 plus 2 nu a0. Okay, and since by assumption a0 is not equal to 0, a2 is also not equal to 0. Put m equals 3 and you get something that you can probably anticipate. A3 equals minus 1 over 3 times 3 plus 2 nu a1. Okay. Remember that all the odd coefficients are now determined by a1, but we have already discussed that a1 is actually equal to 0 for the case r equals nu, which means a3 also is 0. Which also means that even a7 and so on and so forth are 0, which means all the odd coefficients vanish in this series. So all odd coefficients vanish. So I only have to worry about the even guys. So the question is, what are the even coefficients? Well, again, I can figure this out using the recursion relation. We have just shown you that a2 is basically minus 1 over 2 times 2 plus 2 nu. You can keep going like this. So put m equals 4 and you get a4 in terms of a2. Okay, so a4 is minus 1 over 4 times 4 plus 2 nu a2. And this is obviously 1 over 4 times 4 plus 2 nu. And since a2 is 1 over 2 times 2 plus 2 nu a0. Right? So you can build all the even coefficients starting out from a0. So what is this equal to? This would be equal to 1 over. So this would be equal to. So I can pull out a 2 from the first term, 2 from the second term. So this would be a 2 to the 4. Okay. And then I can write a 2 factorial. And I can write this as nu plus 1 times nu plus 2 times a0. Okay. So you can quickly check for yourself that a6 would also have the same pattern. And I can quickly write a very simple formula for all the even coefficients. The even coefficients will alternate in sign. So as you can see, a2 has a negative sign and a4 has a positive sign. So a to the 2n will have a minus 1 to the n. Okay. And then there'll be as many powers of 2 as the coefficient that we are looking at. So there'll be 2 to the 2n. And if you look at this, a2 has a 1 factorial in the denominator, a4 has a 2 factorial. So a2n would correspondingly have an m factorial. And then it will have factors like nu plus 1, nu plus 2, all the way to mu plus n. So write this in a slightly more symmetrical fashion. And this will multiply A0. Okay. So the advantage of writing it this way is that it's very clear to you that we only need to worry about the even coefficients. So in this case, ms1, 2, and so on and so forth. A0 is of course undetermined, and we could always fix A0 by demanding that the solutions have some special property. Okay. So formally, this solves the problem, at least for the root r equals nu. We are done. We have everything that we need. We have discovered that the solution is of the form m equals 0 to infinity, am x to the m plus r. Since r is nu, we have m plus nu. This is the formal solution for the Bessel's equation. And we also have a recursion formula for the coefficients. Of course, here I should actually write this as A to M, because only the even coefficients are allowed. All the odd coefficients vanish. Okay. But before writing it in this general fashion, we now want to see if we can specialize to some specific values of nu, and if we get something out of it. And we do indeed get something out of it. So just like in the case of Lechander's equation, when you took n to be an integer, the series actually terminated. In this case, the series doesn't actually terminate, but you could still write down this solution for the case of an integer nu. Okay, so this is not necessarily the only possibility. You could also consider nus that are non-integers, and we will consider them shortly. But we could consider n nu to be integers. Okay? So integer nu, Bessel functions. What are these? So let's consider nu to be an integer. So nu equals n. N is an integer. Okay. So what is my a to m in this case? A to m would be the denominator is again a 2 to the 2m, m factorial. I'm going to replace all the nus by an integer n plus m. Okay. The numerator, of course, has a minus 1 to the n times a0. All right. So now what should be the choice of A0 such that this series sort of simplifies? Okay, there is no particular reason for choosing this value of A0 that I'm going to choose. For example, I can choose A0 equal to 1. But the problem with choosing A0 equals 1 is that every term in the series is going to look a little unwieldy. So with a proper choice of A0, we can actually eliminate this and write it in a very neat fashion. The way we do this is, of course, if you just look at this, n plus 1, n plus 2 times n plus n, n plus n. Suppose if A0 had a 1 over n, n minus 1, all the way till n plus 1, then the whole thing can be collapsed into a factorial of n plus m. In other words, what I'm saying is the following. Suppose if I choose A0 to be 1 over 2 to the n factorial. Now what's going to happen is that this n factorial in the denominator is going to combine with these factors of n plus 1 times n plus 2 times up to n plus m and convert this into an n plus m factorial. Okay. So instead of worrying about a whole bunch of factors here, I can neatly write this entire thing as an n plus m factorial. So that motivates this particular choice of A0 for. So if you do this, your coefficients A to m are going to look like 2 to the 2m plus n. There is nothing to do about this m factorial, but now the rest are going to collapse into a single n plus m factorial, and we're going to have minus 1 to the n. Okay. There's no A0. I've already used the fact that A0 has been chosen to be this particular value. Again, m is 1, 2, and so on and so forth. Okay. So with this choice of A0, I can write down my solutions, and these solutions I will call Jn of x. Okay. I don't call this Yn of x, I call this Jn of x, a solution of the Bessel's equation for an integer nu. And this is of course given by x to the r is nu, but nu is an integer n, so there is an x to the n out front. And summation n goes to 0 to infinity minus 1 to the n x to the 2n, because only the even coefficients survive, divided by 2 raised to the power 2m plus n, m factorial, n plus n factorial. Okay, and I'm going to assume that n is a positive integer. Okay. So here also I'm going to assume that nu is greater than or equal to 0. Okay. So these Jn's are called Bessel functions of the first kind, which tells you that there is obviously Bessel's functions of the second kind. We will talk about that in the next lecture, of order n. So you could have J0s, J1s, and so on and so forth. Now I invite you to show that this series actually converges, which is something that is easy to show. Okay, so simply look at the ratio test. Take the coefficient of x to the 2m and take the coefficient of x to the 2m plus 2, which is the next term in the series, and divide the first by the second, and then you will, and then take the limit m goes to infinity, and you will actually find that this goes to 0. Okay, so you can actually show by ratio test that Jn of x converges for all x. Excuse me. Okay. So I leave this to you to show. So that's pretty much everything you need to know about Bessel's function, the first kind of order n, assuming that u is an integer n. Okay. So now let us work out the first couple of Bessel's functions. So it's actually nice to see the form of these Bessel's functions. So let's just look at the first and the second. So n equal to 0 case and n equal to 1 case, because these can appear in your problems later when you actually solve for practical applications of these guys. So what is J0 of x? Well, let us put n equal to 0 in this equation. If I put n equal to 0, x to the 0 is just 1. So that goes away. M equals 0 to infinity. There is nothing to do about the minus 1 to the m. I'll just keep it as such. X to the 2m. It's a 2 to the 2m. M factorial times another m factorial, because n equal to 0. So there is an m factorial squared. Okay. If you actually write this out, there is a curious pattern that comes in. So the first term, m equal to 0, is of course just 1, because anything to the power 0 is 1 and 0 factorial is 1. The second term has a negative sign because m equals 1 minus 1 to the 1 has a negative sign. And this becomes 1 over, this is 2 square times 2 factorial square x square. The second term, m equals 2, comes with a positive sign, and this is 2 to the 4, 2 factorial square. So the first term would be a 1 factorial square, because I'm putting in m equals 2. Okay? And this guy is x to the 4. Okay, and then you can easily guess that this term would be 2 to the 6th, 3 factorial square, x to the 6th, and so on and so forth. Now, if you close your eyes to the coefficients out front, this series has a 1 minus x squared plus x to the 4th minus x to the 6th, and so on and so forth. And you already know a series that has this pattern, and that is a cosine series. Okay, so J0 of x in some sense reminds us of a cosine series. Of course, I'm not claiming that this is a cosine series. It is not. It has wildly different properties, but at least the pattern looks like a cosine series. Okay, there's only even powers of x and the signs alternate. So how about J1 of x? Well, if I put n equals 1 here, I'll have an x that multiplies the series. M equals 0 to infinity again, minus 1 to the m, x to the 2m divided by 2 to the 2m plus n, which is 1, okay, times m factorial times m plus 1 factorial. If you actually work this out, you will get x over 2 minus x cubed over 2 cubed times 2 factorial plus x to the 5 over 2 to the 5. I think you will get a 2 factorial. So since I'm putting m equals 2, I'll get a 2 factorial from this term and a 3 factorial from this term, minus so on and so forth. Okay. And you can also recognize that this looks like a sine series. It is not a sine series, but the pattern is exactly like a sine series. But the coefficients of x and x cubed and x to the 5 are totally different. Okay, so if you plot these, you can actually look the plots up in your textbook or any other source, and you would find two things. One, that the zeros of this function j0, j1, or whatever, unlike the cosines and sines, are not in a are not evenly spaced. In other words, like a cosine and a sine looks like this, right? So wherever the function becomes 0, this is neatly evenly spaced, right? But that is not true for the j0s and the j1. So if you plot j0, so you're going to get something like, so since it looks like a cosine function, it's going to start here at 1 x is equal, at x is equal to 0, it has a value 1. It's going to look something like this, but the oscillations are going to die down. Okay, the height of this wave is going to keep decreasing, and the distance between these guys is also not the same. Okay, so properties of these differences, it has the pattern of a cosine series in some sense. Okay, and this is not just an ideal comparison. You can actually work out this pattern, and you can actually show that for large x, okay, so for large x, Jn of x can be approximately written as some 2 over pi x times cosine x minus n pi by 2 minus pi by 4. Okay, so this is something that is possible to write down. Anyway, regardless of this exact equivalence, what I wanted to tell you here is that if I choose nu to be a positive integer, for a judicial choice of a0, the series can be written in a very nice compact form in this fashion. Okay, so once you know the coefficients, of course, you know the entire series, and that is basically the solution for the Bessel equation for this particular assumption. The assumption is that we are looking at r equals nu, and we are specializing to the case where nu is an integer n. Okay. So obviously, the next thing to do is to ask what happens if nu is not an integer. What if nu is not an integer? No worries, we can solve it in this case also. Okay, we will stick to nu greater than or equal to 0, but we don't necessarily assume that nu is an integer. If we do not assume that nu is an integer, we have to go back to the drawing board and write down the formula that we derived for a to m. What was this? This was again a 2 to the 2m, m factorial, nu plus 1, nu plus 2, all the way to nu plus m, minus 1 to the m, a0. M equals 1, 2, and so on and so forth. Right? This is exactly what we had way back here. Right? So this is exactly what we initially had. Now in this case, nu is not an integer. Okay. So now Again, I need to choose my A0 in such a fashion that this guy collapses and the series looks neat. So the question is, what should be my choice for A0? In the first case, the choice for A0 was fairly easy to guess because I saw these factors of n plus 1, n plus 2, etc. If I had a choice like 1 over n factorial, then this is the entire uh, product of these n's is going to collapse to n plus m factorial. But in this case, of course, I don't have a luxury like that because nu is not an integer. So what is the function that can approximate a factorial? Well, such a function does exist, of course, and this is not something that is easy to guess. I'll give you the answer and then tell you how it works. The answer is 1 over 2 to the nu. So far, it's the exact same thing as what we had before, right? It shows A0 to be 1 over 2 to the n. But now I have what is called a gamma function. Gamma of nu plus 1. If you have not seen gamma functions before, don't worry. The definition of gamma function is actually quite simple. And for our purposes, we need only one property of gamma functions. The definition of gamma function, this is the definition, is integral 0 to infinity dt e to the minus t to the nu. Okay, so notice that this is the definition of gamma of nu plus 1. The definition of gamma nu plus 1 has an integral with a t to the nu. Okay, the t is of course an arbitrary parameter that will be integrated because this is a definite integral. Okay. In fact, we can actually do this out and derive a very cute recursion formula for the gammas themselves. So take this to be your du and this to be, sorry, take this to be your, oops, dv, and this to be your u, and apply the udv from formula that you know. This is basically t to the nu minus e to the minus t between the limits infinity and 0 minus integral 0 to infinity minus e to the minus t. And if I differentiate this guy, I would get nu t to the nu minus 1 dt. Okay. Now, if you look at the boundary term, if I put t to infinity, the e to the minus infinity part is going to go to 0. And if I put t to 0, the t to the nu is going to go to 0. So in both these limits, the boundary term vanishes. So this guy basically goes to 0. And I have, this is equal to nu times 0 to infinity dt e to the minus t, t to the nu minus 1. But if you look at the definition of gamma function, the gamma of nu plus 1 is dt e to the minus t with 1 power of nu less in the t. So obviously this guy is therefore the definition of gamma nu. Okay. So gamma function has a nice recursive property that the gamma of nu plus 1 is nu times the gamma of nu. Okay, so this should sort of start reminding you of a factorial because I can keep going in this fashion, right? So I can write this as nu times nu minus 1, gamma nu minus 1, and so on and so forth. Okay, so I'll make this more explicit as I go along. So this is where we are. Okay, so suppose if nu were an integer aside, if nu were an integer n, okay, then what will happen is that I will have gamma n plus 1 is n gamma n. Okay, and this would be equal to n times n minus 1 gamma n minus 1. And I can keep going in this fashion because of this recursion relation. And I will write this as n times n minus 1 times n minus 2, blah, 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 all the way to gamma 1. Okay, and gamma 1 can be easily evaluated because gamma 1 is basically 0 to infinity e to the minus t. Remember that since I want gamma 1, I have to put nu to be equal to 0. So this is just e to the minus t dt, which you can easily evaluate to be 1. So this is basically, since gamma 1 is just 1, This is basically n factorial. Okay. Gamma of n plus 1 is just n factorial. So that is the connection between the gamma functions and the factorial business. Gamma of nu plus 1 would be a simple factorial had nu been an integer. Of course, nu is not an integer, so I cannot apply this, but this is how the gamma function extends the notion of a factorial. So now this choice hopefully is a little more clear. 2 to the nu gamma nu plus 1. Okay. Once I put in this particular choice, my recursion relation gives me a value of the coefficient a to m, and this a to m is basically 2 to the 2m plus nu. The 1 over 2 to the 2m was already there, but there is a 2 to the nu from the a0 part, so that's how we get the 2 to the 2m plus nu. And the a0 also provides me with a gamma of nu plus 1. And the rest is as it is, nu plus 1, nu plus 2, blah, 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 up to nu plus m. And of course, I have a minus 1 to the m on top. Okay. And now you can quickly check again using the same recursion relation that I just gave you, that nu plus 1, nu plus 2, all the way to nu plus m, gamma nu plus 1 is basically gamma of nu plus m plus 1. So again, the presence of this gamma function helps us to collapse this product of nu's. How do I understand this? Well, again, using the recursion relation that I have here, right? Gamma of nu plus 1 is nu gamma nu. So which means nu plus 1, gamma nu plus 1. So look at this factor and this factor. And that can be written as gamma nu plus 2, right? So this sum can now be written as, you start with nu plus 2 now, go all the way to nu plus m, gamma nu plus 2, right? But now combine this and this, because nu plus 2, gamma nu plus 2 would be gamma nu plus 3. So this would be gamma nu plus 3 all the way to nu plus m, gamma nu plus 3. And you keep going this way, and finally you will simply end up with gamma of nu plus m plus 1. Okay. So just like the factorial business helped you to collapse this product of n's, the gamma function helps you to collapse this product of nu's very effectively. So putting everything together, you finally have your coefficients, the even coefficients again, which is now given by 2 to the 2m plus nu m factorial gamma m plus nu plus 1 with a minus 1 to the m on top. Okay. So now that we have the coefficients, we have the series, and this series I'm going to call j nu x. And this is given by x to the r. R is still nu. Okay, we have not changed that. We are still working with the r equal to nu. We have to worry about what happens when r is minus nu later. M equals 0 to infinity. 2 to the 2m plus nu m factorial gamma m plus nu plus 1, that is your denominator, times minus 1 to the m. Of course, there is a x to the 2m. Okay, and these are called Bessel functions of the first kind, again, of order. And just like the case for integers, you can easily verify that this series also converges for all values of x. Okay. So this is the Frobenius method applied to the Bessel's equation. But notice that we're not completely done, right? So we only talked about one root of the integral equation, which is r equals plus nu. We still have to worry about what happens to the other root, and we have to understand what happens. Is there a Bessel function of the second kind? And this will be the subject of the next lecture. For today, I'll stop here, and we will continue with the investigation of Bessel's function in the next lecture.